In electronics, a flip-flop or latch is a circuit that has two stable states and can be used to store state information. A flip-flop is a bistable multivibrator. The circuit can be made to change state by signals applied to one or more control inputs and will have one or two outputs. It is the basic storage element in sequential logic. Flip-flops and latches are a fundamental building block of digital electronic systems used in computers, communications, and many other types of systems. Flip-flops and latches are used as data storage elements. Such data storage can be used for storage of state, and such a circuit is described as sequential logic. When used in a finite-state machine, the output and next state depend not only on its current input, but also on its current state. It can also be used for counting of pulses, and for synchronizing variably-timed input signals to some reference timing signal. Flip-flops can be either simple or clocked. The simple ones are commonly called latches. The word latch is mainly used for storage elements, while clock devices are described as flip-flops. A latch is level-sensitive, whereas a flip-flop is edge-sensitive. That is, when a latch is enabled it becomes transparent, while a flip-flop's output only changes on a single type of clock edge. History. The first electronic flip-flop was invented in 1918 by William Eccles and F. West Jordan. It was initially called the Eccles-Jordan trigger circuit and consisted of two active elements. Such circuits and their transistorized versions were common in computers even after the introduction of integrated circuits, though flip-flops made from logic gates are also common now. Early flip-flops were known variously as trigger circuits or multivibrators. According to P. L. Lindley, a JPL engineer, the flip-flop types discussed below were first discussed in a 1954 UCLA course on computer design by Montgomery Foster, and then appeared in his book Logical Design of Digital Computers. Lindley was at the time working at Hughes Aircraft under Eldred Nelson, who had coined the term JK for a flip-flop which changed states when both inputs were on. The other names were coined by Foster. They differ slightly from some of the definitions given below. Lindley explains that he heard the story of the JK flip-flop from Eldred Nelson, who was responsible for coining the term while working at Hughes Aircraft. Flip-flops in use at Hughes at the time were all of the type that came to be known as JK. In designing a logical system, Nelson assigned letters to flip-flop inputs as follows: number 1, A and B, number 2, C and D, number 3, E and F, number 4, G and H, number 5, J and K. Nelson used the notations J input, and K input in a patent application filed in 1953. Implementation. Flip-flops can be either simple or clocked. The transparent ones are commonly called latches. The word latch is mainly used for storage elements, while clock devices are described as flip-flops. Simple flip-flops can be built around a pair of cross-coupled inverting elements, vacuum tubes, bipolar transistors, field effect transistors, inverters, and inverting logic gates have all been used in practical circuits. Clock devices are specially designed for synchronous systems. Such devices ignore their inputs except at the transition of a dedicated clock signal. Clocking causes the flip-flop to either change or retain its output signal based upon the values of the input signals at the transition. Some flip-flops change output on the rising edge of the clock, others on the falling edge. Since the elementary amplifying stages are inverting, two stages can be connected in succession to form the needed non-inverting amplifier. In this configuration, each amplifier may be considered as an active inverting feedback network for the other inverting amplifier. Thus the two stages are connected in a non-inverting loop, although the circuit diagram is usually drawn as a symmetric cross-coupled pair. Flip-flop types. Flip-flops can be divided into common types. The SR, D, T, and JK types are the common ones. The behavior of a particular type can be described by what is termed the characteristic equation, which derives the next output, Qnext, in terms of the input signal, S, and/or the current output. Simple set-reset latches, Sr Latch. When using static gates as building blocks, the most fundamental latch is the simple Sr latch, where S and A stand for set and reset. It can be constructed from a pair of cross-coupled NOR logic gates. The stored bit is present on the output marked Q. While the S and OR inputs are both low, feedback maintains the Q and Q outputs in a constant state, with Q the complement of Q. If S is pulsed high while R is held low, then the Q outputs is forced high, and stays high when S returns to low. Similarly, if R is pulsed high while S is held low, then the Q outputs is forced low, and stays low when R returns to low. Note, X means don't care, that is either 0 or 1 is a valid value. The R equals S equals 1 combination is called a restricted combination or a forbidden state because, as both NOR gates then output zeros, it breaks the logical equation Q equals not Q. The combination is also inappropriate in circuits where both inputs may go low simultaneously. The output would lock at either 1 or 0 depending on the propagation time relations between the gates. To overcome the restricted combination, one can add gates to the inputs that would convert equals to one of the non-restricted combinations. That can be, Q equals 1 a euro referred to as an S latch, Q equals 0 a euro referred to as an A latch. This is done in nearly every programmable logic controller. Keep state a euro referred to as an E latch. Alternatively, the restricted combination can be made to toggle the output. The result is the JK latch. Characteristic, Q plus equals RQ plus Rs or Q plus equals RQ plus S, Sr NAND latch. This is an alternate model of the simple S latch which is built within NAND logic gates. Set and reset now become active low signals, denoted S and R respectively. Otherwise, operation is identical to that of the S latch. Historically, S latches have been predominant despite the notational inconvenience of active low inputs. JK latch. The JK latch is much less frequently used than the JK flip-flop. The JK latch follows the following state table, hence, the JK latch is an Styradian latch that is made to toggle its output when past the input combination of 11. Unlike the JK flip-flop, the 11-input combination for the JK latch is not very useful because there is no clock that directs toggling. Gated latches and conditional transparency, latches are designed to be transparent. That is, input signal changes cause immediate changes in output. When several transparent latches follow each other, using the same enable signal, signals can propagate through all of them at once. Alternatively, additional logic can be added to a simple transparent latch to make it non-transparent or opaque when another input is not asserted. By following a transparent high latch with a transparent low latch, a master a slave flip-flop is implemented. Gated S latch. A synchronous S latch can be made by adding a second level of NAND gates to the inverted S latch. The extra NAND gates further invert the inputs so the simple S latch becomes a gated S latch. With E high, the signals can pass through the input gates to the encapsulated latch. All signal combinations except for equals hold then immediately reproduce on the output, that is the latch is transparent. With E low the latch is closed and remains in the state it was left the last time E was high. The enable input is sometimes a clock signal, but more often a read or write strobe. Gated D latch. This latch exploits the fact that, in the two active input combinations of a gated S latch, R is the complement of S. The input NAND stage converts the two D input states to these two input combinations for the next S latch by inverting the data input signal. The low state of the enable signal produces the inactive 11 combination. Thus a gated D latch may be considered as a one-input synchronous S latch. This configuration prevents application of the restricted input combination. It is also known as transparent latch, data latch, or simply gated latch. It has a data input and an enable signal. The word transparent comes from the fact that, when the enable input is on, the signal propagates directly through the circuit, from the input D to the output Q. Transparent latches are typically used as I/O ports or in asynchronous systems, or in synchronous two-phase systems, where two latches operating on different clock phases prevent data transparency as in a master a slave flip-flop. Latches are available as integrated circuits, usually with multiple latches per chip. For example, 74HC75 is a quadruple transparent latch in the 7400 series. The truth table shows that when the enable clock input is 0, the D input has no effect on the output. When EC is high, the output equals D. Latch. The classic gated latch designs have some undesirable characteristics. They require double rail logic or an inverter. The input-to-output propagation may take up to 3 gate delays. The input-to-output propagation is not constant. Some outputs take 2 gate delays while others take 3. Designers looked for alternatives. A successful alternative is the latch. It requires only a single data input, and its output takes a constant 2 gate delays. In addition, the 2 gate levels of the latch can, in some cases, be merged with the last 2 gate levels of the circuits driving the latch because many common computational circuits have an OR layer followed by an AND layer as their last 2 levels. Merging the latch function can implement the latch with no additional gate delays. The merge is commonly exploited in the design of pipeline computers, and, in fact, was originally developed by JGL to be used in the IBM System/360 Model 91 for that purpose. The latch is hazard-free. If the middle NAND gate is omitted, then one gets the polarity hold latch, which is commonly used because it demands less logic. However, it is susceptible to logic hazard. Intentionally skewing the clock signal can avoid the hazard. D flip-flop. The D biop is widely used. It is also known as a data, or delay flip-flop. The D flip-flop captures the value of the D input at a definite portion of the clock cycle. That captured value becomes the Q output. At other times, the output Q does not change. The D flip-flop can be viewed as a memory cell, a zero-order hold, or a delay line. Truth table. X denotes a don't care condition, meaning the signal is irrelevant. Most D-type flip-flops in ICs have the capability to be forced to the set or reset state, much like an Steradian flip-flop. Usually, the illegal S equals R equals 1 condition is resolved in D-type flip-flops. By setting S equals R equals 0, the flip-flop can be used as described above. Here is the truth table for the others S and R possible configurations. These flip-flops are very useful, as they form the basis for shift registers, which are an essential part of many electronic devices. The advantage of the D flip-flop over the D-type transparent latch is that the signal on the D input pin is captured the moment the flip-flop is clocked, and subsequent changes on the D input will be ignored until the next clock event. An exception is that some flip-flops have a reset signal input, which will reset Q, and may be either asynchronous or synchronous with the clock. The above circuit shifts the contents of the register to the right, 1-bit position on each active transition of the clock. The input X is shifted into the leftmost bit position. Classical positive edge-triggered D flip-flop. This circuit consists of 2 stages implemented by Sr NAND latches. The input stage processes the clock and data signals to ensure correct input signals for the output stage. If the clock is low, both the output signals of the input stage are high regardless of the data input. The output latch is unaffected and it stores the previous state. When the clock signal changes from low to high, only one of the output voltages goes low and resets the output latch. If D equals 0, the lower output becomes low. If D equals 1, the upper output becomes low. If the clock signal continues staying high, the outputs keep their states regardless of the data input and force the output latch to stay in the corresponding state as the input logical 0 remains active while the clock is high. Hence the role of the output latch is to store the data only while the clock is low. The circuit is closely related to the gated D latch as both the circuits convert the 2D input states to 2 input combinations for the output S latch by inverting the data input signal. The difference is that in the gated D latch simple NAND logical gates are used while in the positive edge-triggered D flip-flop Sr NAND latches are used for this purpose. The role of these latches is to lock the active output producing low voltage. Thus the positive edge-triggered D flip-flop can be thought of as a gated D latch with latched input gates. Master a slave edge-triggered D flip-flop. A master a slave D flip-flop is created by connecting two gated D latches in series, and inverting the enable input to one of them. It is called master a slave because the second latch in the series only changes in response to a change in the first latch. For a positive edge-triggered master a slave D flip-flop, when the clock signal is low the enable seen by the first or master D latch is high. This allows the master latch to store the input value when the clock signal transitions from low to high. As the clock signal goes high the inverted enable of the first latch goes low and the value seen at the input to the master latch is locked. Nearly simultaneously, the twice inverted enable of the second or slave D latch transitions from low to high with the clock signal. This allows the signal captured at the rising edge of the clock by the now locked master latch to pass through the slave latch. When the clock signal returns to low, the output of the slave latch is locked, and the value seen at the last rising edge of the clock is held while the master latch begins to accept new values in preparation for the next rising clock edge. By removing the leftmost inverter and the circuit at side, a D-type flip-flop that strobes on the falling edge of a clock signal can be obtained. This is a truth table like this. Edge-triggered dynamic D storage element, an efficient functional alternative to a D flip-flop can be made with dynamic circuits as long as it is clocked often enough. While not a true flip-flop, it is still called a flip-flop for its functional role. While the master a slave D element is triggered on the edge of a clock, its components are each triggered by clock levels. The edge-triggered D flip-flop, as it is called even though it is not a true flip-flop, does not have the master a slave properties. Edge-triggered D flip-flops are often implemented in integrated high-speed operations using dynamic logic. This means that the digital outputs is stored on parasitic device capacitance while the device is not transitioning. This design of dynamic flip-flops also enables simple resetting since the reset operation can be performed by simply discharging one or more internal nodes. A common dynamic flip-flop variety is the true single-phase clock type which performs the flip-flop operation with little power and at high speeds. However, dynamic flip-flops will typically not work at static or low clock speeds. Given enough time, leakage paths may discharge the parasitic capacitance enough to cause the flip-flop to enter invalid states. T flip-flop. If the T input is high, the T flip-flop changes state whenever the clock input is strobed. If the T input is low, the flip-flop holds the previous value. This behavior is described by the characteristic equation, and can be described in a truth table. When T is held high, the toggle flip-flop divides the clock frequency by 2. That is, if clock frequency is 4 MHz, the output frequency obtained from the flip-flop will be 2 MHz. This divide-by feature has application in various types of digital counters. A T flip-flop can also be built using a JK flip-flop or D flip-flop. JK flip-flop. The JK flip-flop augments the behavior of the SR flip-flop by interpreting the S equals R equals 1 condition as a flip, or toggle command. Specifically, the combination J equals 1, K equals 0 is a command to set the flip-flop. The combination J equals 0, K equals 1 is a command to reset the flip-flop. And the combination J equals K equals 1 is a command to toggle the flip-flop, that is, change its output to the logical complement of its current value. Setting J equals K equals 0 does not result in a D flip-flop, but rather, will hold the current state. To synthesize a D flip-flop, simply set K equal to the complement of J. Similarly, to synthesize a T flip-flop, set K equal to J. The JK flip-flop is therefore a universal flip-flop, because it can be configured to work as an Steradian flip-flop, a D flip-flop, or a T flip-flop. The characteristic equation of the JK flip-flop is, and the corresponding truth table is, metastability. Flip-flops are subject to a problem called metastability, which can happen when two inputs, such as data and clock or clock and reset, are changing at about the same time. When the order is not clear, within appropriate timing constraints, the result is that the output may behave unpredictably, taking many times longer than normal to settle to one state or the other, or even oscillating several times before settling. Theoretically, the time to settle down is not bounded. In a computer system, this metastability can cause corruption of data or a program crash if the state is not stable before another circuit uses its value. In particular, if two different logical paths use the output of a flip-flop, one path can interpret it as a 0 and the other as a 1 when it has not resolved to stable state, putting the machine into an inconsistent state. Timing considerations: setup, hold, recovery, removal times. Setup time is the minimum amount of time the data signal should be held steady before the clock event so that the data are reliably sampled by the clock. This applies to synchronous input signals to the flip-flop. Hold time is the minimum amount of time the data signal should be held steady after the clock event so that the data are reliably sampled. This applies to synchronous input signals to the flip-flop. Synchronous signals should be held steady from the setup time to the hold time, where both times are relative to the clock signal. Recovery time is like setup time for asynchronous ports. It is the time available between the asynchronous signals going inactive and the active clock edge. Removal time is like hold time for asynchronous ports. It is the time between active clock edge and asynchronous signal going inactive. Short impulses applied to asynchronous inputs should not be applied completely within the recovery-removal period, or else it becomes entirely indeterminable whether the flip-flop will transition to the appropriate state. In another case, where an asynchronous signal simply makes one transition that happens to fall between the recovery-removal time, eventually the asynchronous signal will be applied, but in that case it is also possible that a very short glitch may appear on the output, dependent on the synchronous input signal. This second situation may or may not have significance to a circuit design. Set and reset signals may be either synchronous or asynchronous and therefore may be characterized with either setup hold or recovery removal times, and synchronicity is very dependent on the TTL design of the flip-flop. Differentiation between setup hold and recovery removal times is often necessary when verifying the timing of larger circuits because asynchronous signals may be found to be less critical than synchronous signals. The differentiation offers circuit designers the ability to define the verification conditions for these types of signals independently. The metastability in flip-flops can be avoided by ensuring that the data and control inputs are held valid and constant for specified periods before and after the clock pulse, called the setup time and the hold time respectively. These times are specified in the data sheet for the device, and are typically between a few nanoseconds and a few hundred picoseconds for modern devices. Depending upon the flip-flop's internal organization, it is possible to build a device with a 0 setup or hold time requirement but not both simultaneously. Unfortunately, it is not always possible to meet the setup and hold criteria, because the flip-flop may be connected to a real-time signal that could change at any time, outside the control of the designer. In this case, the best the designer can do is to reduce the probability of error to a certain level, depending on the required reliability of the circuit. One technique for suppressing metastability is to connect two or more flip-flops in a chain, so that the output of each one feeds the data input of the next, and all devices share a common clock. With this method, the probability of a metastable event can be reduced to a negligible value, but never to 0. The probability of metastability gets closer and closer to 0 as the number of flip-flops connected in series is increased. The number of flip-flops being cascaded is referred to as the ranking. Dual-ranked flip-flops is a common situation. So-called metastable hardened flip-flops are available, which work by reducing the setup and hold times as much as possible, but even these cannot eliminate the problem entirely. This is because metastability is more than simply a matter of circuit design. When the transitions in the clock and the data are close together in time, the flip-flop is forced to decide which event happened first. However fast we make the device, there is always the possibility that the input's events will be so close together that it cannot detect which one happened first. It is therefore logically impossible to build a perfectly metastable-proof flip-flop. Flip-flops are sometimes characterized for a maximum settling time, In this case, dual-ranked flip-flops that are clocked slower than the maximum allowed metastability time will provide proper conditioning for asynchronous signals. Propagation delay. Another important timing value for a flip-flop is the clock-to-output delay or propagation delay, which is the time a flip-flop takes to change its output after the clock edge. The time for a high-to-low transition is sometimes different from the time for a low-to-high transition. When cascading flip-flops which share the same clock, it is important to ensure that the T-co of the preceding flip-flop is longer than the hold time of the following flip-flop, so data present at the input of the succeeding flip-flop is properly shifted in following the active edge of the clock. This relationship between T-co and TH is normally guaranteed if the flip-flops are physically identical. Furthermore, for correct operation, it is easy to verify that the clock period has to be greater than the sum TU plus a TH. Generalizations. Flip-flops can be generalized in at least two ways, by making them one of n instead of one of two, and by adapting them to logic with more than two states. In the special cases of one of three encoding, or multi-valued ternary logic, these elements may be referred to as flip-flop-flops. In a conventional flip-flop, exactly one of the two complementary outputs is high. This can be generalized to a memory element with n outputs, exactly one of which is high. The output is therefore always a one-hot representation. The construction is similar to a conventional cross-coupled flip-flop. Each output, when high, inhibits all the other outputs. Alternatively, more or less conventional flip-flops can be used, one per output, with additional circuitry to make sure only one at a time can be true. Another generalization of the conventional flip-flop is a memory element for multi-valued logic. In this case the memory element retains exactly one of the logic states until the control inputs induce a change. In addition, a multiple-valued clock can also be used, leading to new possible clock transitions. See also, multivibrator, positive feedback, deadlock, pulse transition detector, latching relay, counter, references. External links. Flip-flop hierarchy, shows interactive flip-flop circuits.